So of the types of ore that occur, they're not all the same. We're going to have a shopping list of a couple of different ways of how these metals occur geologically. They fall into a couple of different broad categories, and they're fairly easy to understand, again, without a lot of geological background. The first one we're going to talk about is magmatic. So you should be thinking about liquid hot magma, right? So I'm going to draw a hypothetical magma chamber. So here we have our liquid hot magma in this. I kind of drew it as a cartoon bubble, but it's really just a conceptual diagram. And it's all molten, kind of. There's some minerals in there, so it's a little bit like a slush, if you're to think about it that way. Kind of a slushy fluid mix. And what happens is the solid minerals that begin to crystallize first. So this thing is slowly cooling off, and some minerals are starting to crystallize. We've met that concept before. Well, it turns out the ones that crystallize earlier are heavier, and they will actually sink down into our into the bottom or the floor of our magma chamber. And so in some areas in our magma chamber, we can get heavier minerals deposited, and some of the more common minerals that will do that are actually chromite. So we'll talk about chromite a little bit later, but also one of the things we'll talk about kind of more recently is magnetite. So chromite, which is a ferroalloy metal, we'll visit those later. We use it to modify iron, but magnetite is actually a mineral from which we get iron, and that's where we're going to kind of be starting our discussion. So magnetite is pretty important. Here you can actually see this is a photo of what we would call a layered mafic complex. This is a really famous one in South Africa, and these are those dark stripes you can see in this picture. Those are layers of chromite, just like we've described here. So now that we've got a magma chamber drawn, we can kind of think about some other ways in which this might happen. So that last category was magmatic, right? So they were deposited from a magma. This next one takes a little bit more thought, although we're still going to use our magma chamber, because if I were to ever design a heavy metal t-shirt or a geology t-shirt that was similar to a heavy metal t-shirt, it would be the fundamental saying that magma sweats metal. Magma sweats metal. Sweaty cheese, right? If you guys think back to our igneous discussion so long ago. So again, as this thing is cooling off, right, it's becoming more and more and more and more solid, right? These crystals are crystallizing. And there's a bunch of stuff. There's water, all kinds of other weird elements that just will never crystallize. And as that mass starts to transition into a solid, it basically pushes those fluids to the outside. So those can be concentrated in veins within the magma itself or within the now solidified igneous rock. So we could get concentrations within these veins here. Additionally, it can actually force fluids out into the surrounding rock, right? So that can be out in these veins, like we would see here. And those just kind of proceed up through the country rock. There's really a couple of different ways that this would occur. I've got a diagram here. This is kind of a scientific diagram. And we'll see this thing a couple of different times, but what it's showing is one of these veins, one of these hydrothermal veins that's working its way from a magma chamber up to the surface. And one of the things that we know is that actually metals will start to drop out at specific temperatures. And so again, we're going to revisit this diagram when we start talking about that. But all of that is really dependent on what the host rock is. So not all rocks are created equal. Some of them are fairly crystalline and they will fracture, like I've kind of been drawing here. Another situation that could happen is maybe over here, again, I'm being just kind of hypothetical. Let's say there's a different rock type. There's a boundary here. And over on this side, these rocks are porous, or like a sandstone or a limestone or something, that as that fluid flows from the magma chamber into those rocks, it doesn't get concentrated in veins, it kind of soaks in like a sponge. And so you'd get mineralization of a very large area, rather than just minerals concentrated in veins. And so those are really the two different ways that we see metals forming as a response to a magma chamber, right? Well, actually three. So we talked about magmatic, piling up on the base, hydrothermal vein. So again, you can see here gold, right? Gold, silver, with cinnabar, right? Mercury. Those are the kind of the three primary ones that we see that come off of this. So that would be hydrothermal vein deposits. Skarn type of deposit, that's a goofy word, we're going to come back to it. Copper is typically deposited this way, and it actually has to do with all of this heat and all this chemistry causing a chemical reaction in the rock itself, right? So rather than the mineral being forced into a fracture and being deposited, it's actually a chemical reaction within the rock. So this next type of deposit is pretty unique. It doesn't happen anymore, although when it did happen, it happened so abundantly that it's a primary source of one of our most important metals. Not one of our most, the most important metal. So for this to make sense, we've got to travel back in time a little bit to the very, very, very early history of Earth and think about what the atmosphere was like. So in the early history of Earth, there was no oxygen in the atmosphere. The atmosphere was comprised primarily of methane and sulfur dioxide, a couple of other really nasty things, lots of greenhouse gases, just a very melty, hot place. That didn't persist, all the way through geologic history, of course. One of the things that we saw happen pretty early is clouds began to form, right? So there's moisture in the atmosphere, there's still no oxygen in the atmosphere, but surface waters begin to accumulate. So very, very early, the Earth is 4.56 billion years old. We have minerals with evidence of surface water at 4.1 billion years, so very early, like chapter 2 in Earth's history is when water shows up. But again, the Earth is a very different place, and minerals will behave differently in the absence of oxygen. So again, if you've taken some chemistry classes, you've learned oxygen is a very hungry caterpillar. It wants to bond with everything. Famously, iron, right? Iron oxidizes, right? Meaning it reacts with oxygen. But if there is no oxygen, that doesn't work out. So iron, in its anoxic condition, without oxygen, is actually what we would call soluble. It will just dissolve in water the way that salt will dissolve in water, or sugar in your tea, right, in your warm tea. It just disassociates, and those minerals and those elements are just part of the fluid. So in very early Earth history, iron-bearing minerals that are here on the continents are decomposing and being eroded by rainwaters, and they're flushing out into the oceans, and the oceans are filled with just free, soluble iron. If you're not familiar, Fe is the chemical symbol for iron. So I'm just drawing these little iron atoms floating around here in our kind of primeval ocean. The oceans would have been red at this point, which is really interesting, or kind of greenish, and then they ultimately turn red. So they're kind of greenish, which is the anoxic version of iron in the redox system. They will be turning red here pretty soon. So green oceans, weird time on Earth. And then what happens is eventually we get abiogenesis. That's not what we're talking about in this class, but I've got another class we talk about that a lot. Essentially, life shows up. Life shows up at, chemical signature of life shows up at about 3.6 billion years ago. The oldest actual fossil that we can hold, I think, is maybe 3.4 billion years ago. And it's a little slime ball. It's a slime ball that kind of looks like so. And what it is, it's a colony of little algae. It's like an algal mat. And we call these things stromatolites. So these stromatolites begin forming on Earth, and they form in these coastal areas, right? So these kind of beachy environments, and the stromatolites are made out of, they're colonies of bacteria. That bacteria, cyanobacteria, blue-green algae. And these are the first things on Earth that begin to photosynthesize. Hopefully you remember from, I guess, junior high what that means. Photosynthesis is essentially the process of taking in carbon dioxide and taking in solar energy and converting that to energy to use and mass and releasing oxygen. So as a function of these stromatolites, we start to see oxygen being released into the atmosphere. Free oxygen, not bonded with carbon, right? So O2 molecules start to fill the atmosphere. Hungry, hungry hippo, or hungry, hungry caterpillar. Pick your favorite children's book or game, I guess. So as oxygen starts to fill the atmosphere, one of the first things that happens is it begins to bond with iron, and it actually forms Fe2O3 and Fe3O4. Those are both different molecules. One of those is magnetite, one of those is hematite. But now, once oxygen has bonded with these iron molecules, it comes out of solution, right? It's the opposite of dissolving. And it begins to pile up on the bottom of the seafloor, these massive, massive, massive layers of what we call banded iron formations. So these banded iron formations, we actually see these almost everywhere on the planet. And because they're so massive, they're these alternating layers. You can actually see a picture here. This is a place where they're a little bit squished up, but you can see these dark silvery layers are actually the mineral hematite, Fe2O3. And because there's so much iron contained, and all we have to do, remember, if we want that iron, and it's Fe2O3, all we have to do is figure out how to break that chemical bond, take the iron, and release the oxygen. Well, again, we'll get into that. So we see these banded iron formations all over the place. Like I said here, you can see in this picture. We're going to come back to these, but this is really the only kind of major discussion we're going to have on how those work. The last type that we're going to talk about, our last type of deposit, is what we call supergene enrichment. And really, it's kind of a combination of a couple of other things. So first of all, we have to have a vein in place, right? So we've got an ore vein, but maybe that ore is a very low quality. Maybe that ore is, 3% of the metal that we're interested in, and we can throw some economics in there. Let's say that metal is not recoverable unless it's 5 or 6%, right? Because you get more money for higher percentage ore, which means you can go after more stuff. So in the case of supergene enrichment, essentially what happens is we have an interesting interaction between groundwater. So this line that I'm drawing here is going to be the water table, or the surface of the groundwater. And everything above that is above the saturation zone. And then we also get atmospheric, or what we call meteoric water, right? Water from meteorology. And this is this is a really interesting thing. So what happens when rainwater falls through the atmosphere is something you've potentially heard of. So let's look at the chemistry here. H2O, right? Another thing that this will interact with as it passes through the atmosphere, remember the atmosphere is mostly nitrogen, about 20% oxygen, but in third place is this funky little guy, CO2. And actually, H2O and CO2 will undergo a chemical reaction as rainwater is falling through the atmosphere and produce H2CO3, which is actually what we would call carbonic acid. It disassociates and forms an acid, which means it can dissolve stuff. So you hear the term acid rain. Well, rain is naturally acidic. It's just a regular thing that happens. But the rate at which this forms is related to how much CO2 there is. So if we're upping our CO2 content, the rain becomes more acidic. Pretty straightforward. But we're not thinking about that stuff right now. We're thinking about these acids dissolving metals, which is what they do. And so we get this kind of upper zone here where the metals are depleted, right? So these are where the metals begin to dissolve. But those waters are carrying the now dissolved metals further down. And when they meet the groundwater, there's some interesting chemistry that occurs there. When they're kind of just slightly above it, there's also a different set of chemistry. You can actually see this is pretty much what I'm trying to draw, but if we look over here, you can see this is a diagram of how a supergene enrichment works. And essentially, as you can see on that diagram and what I'm going to highlight here, the ore in this part of the vein now has a very high or enriched concentration. So the stuff here at the surface is depleted, but it's all kind of redeposited further down. And actually, famously, this upper portion is kind of weird, insoluble stuff left behind. It tends to be kind of earthy red color. We call it Gossin. Miners back in the day would just look for Gossin and then go down and hopefully find that supergene enrichment. Then pull metals out of there and buy a fancy house on the hill and call it good. Okay, so that's going to finish our big metals overview. We're going to further categorize these things, although you've basically met how it's all going to work. But we're going to focus on different groups of metals as we move forward. So that's what you see finishing up with specialty metals. All right, well, we'll go ahead and see you in the next video.